In this video, we will learn how cycloalkanes and more specifically cyclohexanes undergo conformational changes. So, if you recall from drawing six-membered rings, there are two potential views we can take on the molecule. The first is a bird's eye view, which I'm also showing in computational form here, and in line angle drawing here. And then the second view is to take kind of the side-on perspective view. And if I move my computational model, that's the view that I'm getting. Right? And so the bird's eye view is nice and symmetric and makes our life easier when drawing. The perspective view gives us a more realistic image that there is kind of an up and down nature to the cyclohexane ring. This kind of perspective view drawing that I have is called the chair conformation of cyclohexane. It's also the chair drawing. Basically, the chair conformation is the lowest energy conformation of cyclohexane, and that's why we always going to draw the perspective in this chair form. And so, drawing the chair conformation can be a bit of a challenge, so I'll try to give you some tips for doing that. So if I just look at the chair conformation, there's a few things to notice. So one of them is that opposing bonds are going to be parallel. So they're in orange. I'll highlight this one in red. And finally this one in blue. So just in terms of making things look nice, you try to get these bonds that are opposite of each other to be parallel to each other in your drawing. There's different ways that people approach the drawing. I feel like there's a number of people who kind of draw V's like this. So like that, and then draw two parallel lines out and then kind of close off the cyclohexane with the third V. Other people like to draw the bottom V, so maybe like this and then like that, and then closing off the sides of the cyclohexane. And still other people may even start from the middle parallel lines and then kind of draw in their V's like so. Whichever way works for you is the way that is the best. So beyond just the cyclohexane chair itself, there's all these groups that are attached to the cyclohexane, and organic chemists are very peculiar and specific about exactly how those groups are drawn. So if we look at the computational model here, and I kind of tilt it a little bit, what you can see is that there's some groups that are going up and down, they're kind of above and below the plane of the cyclohexane. And there's some groups, so these hydrogen atoms, that are in the plane of the cyclohexane. And so we categorize those two different types of groups in the chair form differently. We call those being either equatorial or axial. So you can kind of think of a globe, right? Think of the globe having a vertical axis, that's an axial group, and then it has an equator along the middle called an equatorial group in the cyclohexane. So back to the chair form. So those axial groups will look like this. So in red there. So these are trying to show the vertical groups in the cyclohexane. I'm going to move my model back to being a chair form. And so you can kind of see that there's on this carbon and then skip a carbon to the next one, that's the same, and then you skip a carbon to the next one, that's the same. So this pattern will show up in cyclohexane a lot. Every other carbon kind of looks the same. And neighboring carbons will have kind of the opposite direction in their axial groups. Right? So if you have axial up on this carbon, then you have axial down on this carbon. Another thing to see is that it's important that on this leftmost carbon in this chair form, this group is always going to be axial down. So my tip for that is that if you look at your cyclohexane chair form, you follow the kind of the direction. If I'm looking at that outermost corner, this is kind of pointing downwards, so then that tells me that my axial group has to be this way. In addition to the axial groups, of course, we have these blue equatorial groups. And so those are all drawn in very specifically. You might notice that the bonds are also parallel. So this bond is also parallel to this bond in this cyclohexane chair form. That's parallel to the equatorial hydrogen all the way on the other side. Right? So there's a lot of parallel bonds in the chair form drawings. when you're trying to draw in these equatorial groups, my view is to always figure out where your axial groups go and then put in your equatorial groups 120 degrees away from the axial group. So in my drawing down here, I have the axial group going down, which I figured out by looking at that corner of the cyclohexane, and then I will go 120 degrees away from that to put in my equatorial group. So that forces it to slant upwards. And so what you kind of see here is that if this carbon has an equatorial slanted up, the next carbon over will have its equatorial slightly slanted down. The next one will have its equatorial slanted up, and so on and so forth, right? All the way around. So again, in the equatorial groups, there's this up, down pattern. So definitely we want to be able to reproduce this drawing pretty specifically. We want to be very accurate about the either up or downness of the axial groups and the up or downness, I guess the up or downness of the equatorial groups. One thing that can be very confusing for students is that I've said axial up and axial down, and the confusing thing is that you'll go back to the bird's eye view drawing and think about up and down from kind of a wedge or a hash perspective, and those are not the same thing. It's very important to keep those separate in your mind, that the bird's eye up and down is different from the chair form up and down. So if I go through, I've drawn in the axial hydrogens on this bird's eye drawing as if my eye was way up here looking down on that chair form. So these three hydrogens are closer to my eye, and those three hydrogens are further away than their respective groups on the carbon. And so that means that all the axial hydrogens are not all wedges or all hashes. There's 3 wedges and 3 hashes. Here it's really easy to see this alternating pattern of every other carbon having kind of the same directionality of its groups. But again, just because a group is hashed here or wedged here doesn't mean that it's necessarily axial or equatorial. If I go and put in the equatorial groups, then they would look like this, right? So for every axial group, there's an opposite equatorial group. If there's a wedged axial group, there should be a hashed equatorial group. If there's a hashed axial group, there's a wedged equatorial group, right? And at the end of the day, you can't get that information from the bird's eye view. You don't know from this drawing whether I intend to tell you that the hydrogen is axial or equatorial. We'll talk about in a few minutes how to determine all of that. An important feature of cyclohexanes is that there's not just one chair conformation. The chair conformation can undergo a flip and enter another equal energy but different chair conformation. I've shown that here in drawing, so I have the chair as I drew previously, undergoing equilibrium or a chair flip, and now I have kind of what looks like the mirror image of the chair, but it's important to understand that this is not the mirror image, but rather an actual conformationally different molecule. So let's look at what this looks like in computational form. So I have my cyclohexane here in the chair conformation. I've tried to select the hydrogen at the very left here, this equatorial hydrogen. And let's follow it as we animate it. And what you see is that it goes from being equatorial and eventually flips up to being axial. So in the computational version right now, you can't really see the second chair form that I've drawn here. But let me turn my drawing just ever so slightly by about 30 degrees. And now you can kind of see the second chair form. Okay? So what's happening when we do the chair flip is we do the chair flip, and then in our drawings we have to rotate just slightly to get to the perspective that we're drawing. And so again, these are not mirror images of each other. I know that because I followed the hydrogen from left to right and it changed from being equatorial to being axial. And so that means they can't be just directly mirror images in the same thing. There is an actual physical process going on. So this is always true. When you do a chair flip, the groups or substituents attached to the ring will undergo a change from being either axial to equatorial or equatorial to axial. I can show you that also drawn out here. So we're kind of having to be able to see that if I look at the groups on either corner, on the leftmost or the rightmost corner, undergo a chair flip, then it looks like this. I want to also pull this up in a physical model form. So here I have a model kit version of cyclohexane with an axial red group and an equatorial blue group. And again, kind of when you're setting up your model, This will work with any type of model kit, but just follow where the axial groups are. You want to set it up so every other carbon has its groups axial in one direction, and that will kind of force every other carbon to have its groups axial in the other direction. If you're starting from the model and you build a flat six-membered ring like this, so like if you purposely make it flat, with many models you'll feel resistance, like this is actually not very stable feeling. And the way to get from this to a chair form is to, again, start from it being completely flat and then bring one of the carbons, so I'm going to bring the left carbon here, that you can see right there, down. And then I'm going to bring the opposite carbon of it, so kind of, if this is the one carbon that I brought down, then it's 2, 3, the 4 carbon that I would then bring up. And that will typically twist your model into a chair conformation. And so if you take that and you want to do a chair flip, I just did that really quickly, but you basically do the opposite. You take opposite ends of your cyclohexane. It actually doesn't matter which opposite ends you take. And then if it's kind of slanted up, you bring that one down, and if it's slanted down, you bring that one up. That will accomplish the chair flip. And you can kind of see the red and blue groups there undergoing this change from here, red being equatorial, to after the chair flip, red being axial. It turns out that this is a somewhat simplified picture of what's actually going on in the real world. The actual chair flip is a number of different processes all linked together. So if we actually look at it, you get to something that looks like this. So what we have is you start with a chair conformation. It can go a little bit into a half chair conformation. That can then turn into a twist boat. That then turns into a boat, where you kind of have both corners here facing up, and then it kind of undoes all of that in the opposite order and gets you to the other chair form. So that's a lot of different conformations, and again, for us, the most relevant ones are the chair conformations at either end here, but I just want to point out that there are many other different kind of intermediate conformations that the molecule has to go through in order to actually undergo a full chair flip. So a question you can always ask when there's multiple conformations then is, well, how do we know, or why is the chair the one that's lowest in energy? And it is actually much lower in energy. So if we're looking at this, what we find is that the half chair is 10 kilocalories per mole higher in energy. The twist boat is 6.5 kilocalories per mole higher in energy. So it doesn't quite fit there. And the boat is 5.5 kilocalories per mole higher in energy than the chair form. Right? So that tells us that cyclohexane would be very appropriate to draw in chair form. That's definitely how the molecule will be found the vast majority of the time. So I'm going to bring up my cyclohexane here, and it'll actually help to draw cyclohexane in Newman projection form. You might wonder how you do that when it's a ring instead of just kind of a chain. And what we do is to take a perspective along two of the parallel bonds. So I'm going to take those two bonds right there, and I'm going to view it like this. So now I have two eyes apparently, and I will look down those two red highlighted bonds, and I will draw a Newman projection for each of those. And what you'll get looks like drawing right there. And so what you see is that this equatorial blue hydrogen on the left here, that is this equatorial blue hydrogen in the Newman projection. And the gray one out here is this one there. The red one in the back here is the red one down there. So hopefully that helps you orient a little. And so you should recognize that the chair conformation puts the single bond between the two carbons into a staggered conformation. And so since in linear alkane chains, staggered conformations were the lowest in energy, the reason that the chair conformation is lowest in energy is because it is able to find the staggered conformation. So it's a collection of staggered conformations of CC bonds together that happens to make a chair. In the same way that we thought about linear alkanes as having kind of an energy raising explanation and an energy lowering explanation, we can look at the higher energy conformations and identify energy raising. If I look at the half chair in Newman projection form, I get a drawing that looks like this one, where I'm highlighting these 4 atoms out here. Those are kind of supposed to represent kind of the planar nature of the half chair over there. And the big thing to notice is that that forces these four hydrogens to be eclipsed with each other. And so that's definitely very high in energy. That's responsible for this 10 kilocalories per mole of high energy. In the boat and the twist boat conformations, the additional interaction that you have is a repulsive one, so a steric repulsive interaction. And that is between kind of the two groups, or the two hydrogens, that are pointed inwards from the two carbons here. So for energy stabilization reasons in the chair, staggered is more stable. And because eclipsing is less stable, and because steric repulsions are less stable, that kind of all adds up to make the chair form the most stable conformation. Of course, that was just cyclohexane. What happens if you put a group onto cyclohexane? And really, when that happens, then you have a question of which chair form is preferred. Because, so for example, if you have methyl cyclohexane, you could either draw that with the methyl group axial or with it equatorial, and those will be related by a chair flip. It turns out the way to decide this is to understand what the source of strain in cyclohexane is. So cyclohexane is not a strain-free molecule, it just has less strain because it's staggered. The chair form still has some amount of strain in it that's called 1,3-diaxial strain. And so I've shown you 3 of the axial hydrogens here. Those are kind of in this 1, 2, 3 arrangement, so kind of this every other carbon type of a view. So the hydrogens in the 1 position and the 3 position, those are so axial up, kind of parallel, they're close enough that there is a little bit of repulsion. That is a little bit of strain right there. So whatever the groups are that are axial, those are the ones that are going to be experiencing some amount of repulsion with the other axial groups, 1,3-diaxial strain. So then naturally, because of this, different sizings of groups being axial will lead to different amounts of strain, and then that should lead to different amounts of preference. You can sum up all of this and quantify it using what's called an A value. So I'll pull up a table here. So in this table of A values, what you're looking at is a number that's trying to quantify how much more stable the equatorial chair form is than the axial chair form given a certain substituent on the cyclohexane ring. So just to look through this, it kind of makes sense that a methyl group has some amount of preference for being equatorial because a methyl is larger than a hydrogen. Once you get to this group right here, so this is tert-butyl, this is a very sterically large group that gets a very large A value. That means that a cyclohexane that's tert-butyl should be found almost exclusively with the tert-butyl group in equatorial position. Let me give you an example here. So if I have a phenyl cyclohexane, again, I can have this equilibrium between axial phenyl group and equatorial phenyl group. I can go through and find that we have an A value of 3.0 that's related to kilocalories per mole. And if we use a neat rule of thumb, which is that for every delta G equals 1.36 kilocalories per mole, that's going to be 1 order of magnitude difference in equilibrium constant K. So we can use that to estimate that in this molecule, phenyl cyclohexane, the chair conformation, the axial phenyl group, will be maybe 1 to 100. Because if each 1.4-ish kcals is worth 10 times equilibrium, then we have 2.8, almost 3 there. So that should be 10 times 10. That gets you to 100 to 1 ratio. Naturally, things get more complicated if there are more groups on the cyclohexane. And the A values turn out to be additive for this situation. So let me pull out the table again. And let's look at an example. So this is dimethyl cyclohexane, and I have it as the trans or anti isomer here. The way that we treat the A values is that we just add them up. So on the left here, the one methyl group axial must be kind of worth the 1.7 kilocalories per mole. The other one is also axial, so another 1.7 kilocalories per mole. On the right, there are no axial groups, so I have no A values to contribute, which means that overall my delta A value is negative 3.4 kilocalories per mole. That would then lead me to predict that the equilibrium constant should be over 10 to the 2 in favor of the right side. You can go through the math and find that it'll be a few hundred. KEQ will equal about a few hundred. Let's look at another example. So now let's put two groups on there, this time an isopropyl group on the left and an alcohol group here on the right. And what I've done here is to have one of them be axial and one of them be equatorial, so that in either chair form there's always a group axial. And so a major question that we'll often ask is which one of those chair forms is more common or more prevalent and more indicative of what the molecule actually looks like if you were to just take a picture of it. So same thing, I'm going to go through and find A values. The alcohols in the axial position is worth 0.87 kilocalories per mole. The isopropyl group in the axial position is worth 2.15 kilocalories per mole. That leads me to 1.28 kilocalories per mole as a value for the delta A value. And then that allows me to predict that the equilibrium constant here would be about 1 over 10, because now we're favoring the left side of this equilibrium. Now this math seems great and seems like an easy way to deal with organic molecules, but there are other effects that can override this math. Just to give you an example of this, if I give you a drawing of this molecule with two very sterically large groups next to each other, you might expect that we should have them be both equatorial instead of both axial, because that's what the A values would tell you. The problem here is that if you put two terbutyl groups equatorial, that means that you're essentially doing a Newman projection that looks like this. I even have to erase to make things fit. And so the point is that actually there's a lot more extra strain that's being put into this molecule in the equatorial or di-equatorial terbutyl group situation. And so this is not something you could quantify for using the A values. It's something that people have observed and had to go back and think about why this had happened. So in this video we kind of talked about cyclohexanes and their conformations, and we looked at how to draw them, how to make sure our groups are placed axial or equatorial, and then how to use an A value table to determine which conformation of cyclohexane is preferred.